Question 1 from the Higher Physics Examination Paper 1 from Qualifications Scotland. A car is travelling at 50 metres per second along a straight road. The brakes are applied and the car comes to a rest in a time of 6 seconds. The distance travelled by the car during the time is, and you're given the usual responses. Two equations we use here. To start off this exam, we use the fact that the average velocity v is equal to the starting velocity plus the final velocity, all divided by 2. Once you find the average velocity, you can then find the distance travelled. It's just simply the average velocity times the time. Okay, let's work out the average velocity. And the average velocity is going to be equal to the starting velocity, which is 15 metres per second. Leave out units for the moment. Plus at rest, when it comes to rest, is 0. And we're dividing that by 2. So we get the average velocity of that car to be 7.5 metres per second. Now once we get the average velocity, it's a simple case of putting into distance is equal to average velocity times time. So we have 7.5 metres per second multiplied by the time, which is 6 seconds. And that's going to give us an answer of 45 metres. So the answer to the first question is 45 metres. It's going to be answer A. Now you could have done that by working out the acceleration and then using the other kinematic equations, but this is a much simpler method. It's an easy method to start off with the higher physics exam. Average velocity is the starting velocity plus the final velocity divided by 2. Once you find the average velocity, you can find the distance by saying distance equals average velocity times time. Question 2. A falling object travels at its terminal velocity because, and you're given the responses. Well, first of all, what is terminal velocity? Terminal velocity is the state of an object that's falling when it's not going to accelerate anymore. It stays at that particular velocity. So we're looking for a diagram which is going to have the weight and the resistance force completely balanced. If I can just draw that little diagram here, you can see that's what we've got. And once an object reaches terminal velocity, we have the following. We have the weight acting down the way. We know that's going to be equal to mg. And there's going to be a resistive force acting up the way, which we'll just call Fr, the resistive force. Now, for the situation where we have terminal velocity, there's no acceleration. Therefore, the unbalanced force acting on it must be equal to 0 because the force of resistance balances the weight of the object coming down the way through the air. So let's look at responses in turn. Response A, the air resistance is less than the weight of the object. Well, if the air resistance is going to be less, this black arrow is going to be smaller, black vector is going to be smaller, therefore the weight is going to be bigger down the way, it's going to accelerate down the way, so that's not going to be the proper answer there. The air resistance is balanced by the weight of the object. Yes, that's correct. The air balance, the frictional force due to the air balances the weight of the object. Therefore, you're going to get no unbalanced force. Therefore, you're going to get a case of no acceleration. You've reached terminal velocity. So that's the one which is correct. We'll just go through the other three just to ease our minds. The air resistance is greater than the weight of the object. Well, if that's the case, then the resistance would be lifting the object up the way because the unbalanced force would be in the upwards direction. So that's obviously wrong. The acceleration of the object is 9.8 meters per second every second. That's a tricky one. We know all objects accelerate at that acceleration, but the unbalanced force is going to be 0. You're going to have no acceleration. So that's going to be wrong. The acceleration of the object is greater than 9.8 meters per second every second. Once again, the answer is wrong because in this case we've got the two forces balanced at terminal velocity. Unbalanced force equals 0, no acceleration. The object will be moving downwards with a constant velocity. So 2, answer is B. Question 3. A cyclist is freewheeling down a slope. The slope is at an angle of 15 degrees to the horizontal as shown. And the cyclist and bicycle have a combined mass of 70.0 kilograms. The component of the combined weight of the cyclist and bicycle acting down the slope is your famous one, the force down the slope. There's the force there, and we know the force has the following value. We know we can say that the force acting down the slope, which is the component of the weight acting down the slope, is equal to mg. That's the weight part, and of course you have to have sine theta. It's in the relationship sheet. So all we have to do is plug in the numbers for that. The force parallel to the slope, the component of weight parallel to the slope, is going to be the combined mass, which we know is going to be 70.0. multiplied by 9.8 gravitational field strength times sine of the angle 15, so sine of 15 degrees. We plug that into our calculator and we get an answer of 177.54 newtons. That'll be the answer of the calculator. Now, it's not in the actual responses, but remember, we are dealing with two significant figures here, 15 degrees. We're dealing with three significant figures here, so we go to the lowest significant figures. We'll have to have two significant figures, so it's going to be, first parallel is going to be 180 newtons to two significant figures, and that'll be the answer in the actual responses. So we have C for our response. Question 4. A trolley of mass 3.0 kilograms is travelling along a level bench towards a stationary trolley of mass 2.0 kilograms. The speed of the 3.0 kilogram trolley just before it collides with the 2 kilogram trolley is 5.0 meters per second, and after the collision the two trolleys stick together and the effects of friction can be ignored. Which row in the table gives the total kinetic energy of the trolleys immediately before the collision and the total kinetic energy of the trolleys immediately after the collision? Well, in order to work out the kinetic energy, we've got to know the velocity of it. We know the velocity before here, but we have to find the velocity of the two trolleys after the collision. So as always, we do a quick sketch of what's happening in rectangle form and fill in all the particular details. We know that that's going to be moving at 5 meters per second, so we put in there 5 meters per second. It's moving in that direction. It's got a mass of 3 kilograms. We can put in 3 kilograms there. This trolley here is not moving at any speed, but it's got a mass of 2.0 kilograms. And then after the collision, which is after the right hand side of this dotted line, the two trolleys are stuck together, so we've got a combined mass of 5 kilograms. And we don't know the speed of it, but we have to find the speed to find the kinetic energy. So, total momentum before, we can work out each momentum together. We know that we have got the total momentum is going to be 3 times 5 in that direction. Plus 0, and after collision the total momentum is going to be 5v. For 3 5s are 15, so we'll get 15 plus 0 and we'll get 5v here, and we know that the total momentum before should equal total momentum afterwards. So we've got a little equation here. We'll get 15 equals 5v, and that implies that v is equal to 3 meters per second. It's a positive number, which must mean it's going in that direction. So we can change that now. We can fill in a diagram. It's now going to be moving at 3 meters per second, and it'll be going to the right as usual. And we've got 5 kilograms. So that's the total momentum. Now we've got to consider now the kinetic energy of these situations. So we can just rub out our working for this, not an exam, keep that working in for exam, but we can rub this out now and do our kinetic energy before and after. Remember, kinetic energy is a scalar, so it doesn't matter which direction you're going in, and the total kinetic energy before this is 1/2 times the mass times v squared for each one. But since this trolley here is not going with any speed, speed 0, it's got no kinetic energy, therefore the total kinetic energy before is going to do 1/2 times 3 times 5 squared. So 1/2 times 3 times 5 squared is going to give you 37.5 joules of kinetic energy. After the collision, we have this situation, EK, once again, is equal to 1/2 mass times speed squared, and we know it's going to be 1/2 the total mass now, 1/2 times 5 times 3 squared. So we do that, we get a value of 22.5 joules. So you can see we have lost kinetic energy at collision. But if we look at the table, we don't see 37.5 or 22.5 because once again we have to round it up to two significant figures. So 37.5 to two significant figures will turn out to be 38 joules. Two significant figures. 22.5 will turn out to be 23 joules. So there we have it. We have got the total kinetic energy before the collision is 38. So we go down the table, we either get C or D. And after collision, it's got to be 23. So the answer to that one has got to be C. Question 5. A toy car of mass half a kilogram, 0.50 kilograms, is travelling along a frictionless track with a constant speed of 0.8 metres per second. A constant force of 1.2 newtons is now applied to a toy car in the same direction as the car is travelling for a time of 1.5 seconds. The change of speed of the car is given by this following responses. Okay, let's look at the car itself. There's the car there like that. It's giving a force over a given time. That is going to be an impulse, and the impulse is going to be F times t. So we can put that in the above the arrow. That's going to be the impulse, which is also equal to the change of momentum of the car. And we know that the impulse is going to be a force of 1.2 times 1.5 seconds. So that's going to equal to 1.2 for the force times 1.5 seconds. And we're going to get an impulse of the following order, 1.8 Newton seconds. Now that corresponds to a change of momentum of 1.8 kilogram meters per second. So we know the change of momentum is going to be that value there. The mass of the car before, we know it's going to be 0.5, so we can fill that in. We can say 0.5 kilograms. And we know it's going to be moving at the following speed. So we're moving at 0.8 meters per second. 0.80 meters per second. So we can work out what the change of work out the momentum of the car is, and then apply the change momentum, because we know that the change momentum delta P is equal to mv minus mu. That's the initial momentum, take away the final momentum. Okay, we know the mass of the car, so we can take out a common factor here. Delta P is going to equal to m into v minus u. Now v minus u is the change of speed. V minus u is going to be equal to the change of speed. So all we have to do is put in the numbers into that little equation there. We know that delta P is going to be 1.8 kilograms meters per second. That's going to equal to the mass of the car, which is going to be 0.5. And we've got this expression here, which is the change of speed. And therefore, just rearranging, change of speed, v minus u, is going to equal the change of momentum divided by the mass of the car, 0.5, which is going to come out to be 3.6 meters per second. 3.6 meters per second. It's the old impulse one. Give an object an impulse, that means a force over a given time, and work that out to give you the impulse, and the impulse is exactly equal to the change of momentum. Once we know the change of momentum, we know the formula, we can take out the common factor m here and get the change of momentum is equal to mass times the change in velocity. Plug things in and we get our final answer. So the response to that one is going to be 3.6, and that's going to be C in our responses.